Alright, Assalamualaikum and hello everyone. So for this session, we're going to learn on a new chapter called Eigenvalue and Eigenvector. And for this topic, we're going to look at characteristic equation. So let's consider a 2-degree of freedom system. This is a wall. Since it is a 2-degree of freedom system, we'll have two masses in one direction. And here we have first spring and second spring K2. So if you watch my previous video on how to develop equation of motion for this kind of 2-degree of freedom system, since we have two mass, so we will have the equation of motion consists of m1 x double dot 1 plus k1 plus k2 x1 minus k2 x2. So let's write this as equation 1, and m2 x double dot 2 minus k2x1 plus k2x2 equals to 0. So this is also equals to 0 because it is a free vibration system. So how do we develop characteristic equation from this? So again, if you don't know how to develop this equation of motion, so please refer to my other video on how to develop equation of motion. So basically, for eigenvalue and eigenvector, in the end is that we want to change the system to be in terms of matrix A minus lambda matrix identity. Okay, so from here, what we need to do first is that we need to divide. So basically from 1, so divide with m, the mass itself. So equation 1 will become x double dot 1 plus k1 plus k2 over m1 x1 minus k2 over m1 x2 equals to 0. So let's write this as equation 3. And from equation 2, we divide with the respective mass, which is m2. So the equation would become x double dot 2 minus k2 over m2 x1 minus k2 over, plus k2 over m2 x2 equals to 0. So let's write this as equation 4. So from these two equations, okay, from equation 3 and 4, we need to convert it into matrix form. So in matrix form, I believe most of you know how to convert this set of linear equations to matrix form. So we will have 1, 0, 0, 1, x double dot 1, x double dot 2, plus we'll have the k over m matrix multiply with x1 and x2, and this is equals to 0. So put it in the value. So k1 plus k2 over m1. So this is minus k2 over m1 minus k2 over m2 and k2 over m2. So matrix 3, equation 3 and 4, okay, we convert it into matrix form. And from this matrix form, okay, in vibration, so we need to assume harmonic motion. So what does harmonic motion give us? So harmonic motion is x equal to v, which is the amplitude sine omega t. So what we're trying to do now is that we're trying to make sure this matrix and this matrix to be equal so that we can solve the whole system. Okay, so we're going to replace this matrix and this matrix for it to be the same, because at the moment this is second order and this is only x, so we can't solve it. So in order to solve it, we need to change it into something. So this is what we're going to do by assuming harmonic motion. So x equals to v sine omega t. So if you differentiate one time, it's going to be omega v cos omega t. And if you differentiate it another time, it will become negative omega squared v sine omega t. So what we're going to do now is we're going to replace this into this, and we're going to replace this term into this. So the matrix is going to be 1, 0, 0, 1. So since this is x double dot, so it has become negative omega squared sine omega t, where I put the v at the back. And since we have x double dot 1, so this will become v1. And second one is to replace x double dot 2, so this become v2 plus k1 plus k2 over m1 minus k2 over m1 minus k2 over m2 and k2 over m2. And now matrix X doesn't exist anymore because we change it with this. So X1 will become V1 sine omega t, and X2 will become V2 sine omega t. And this is equals to 0. So if you remember, I mentioned that we want this matrix and this matrix to be equals. They have to be the same so that we can try to solve it. So mathematically, we can cut this off, sine omega t. Okay, this is constant. And in the end, what we're trying to do is that we're going to left out v1 and v2. And if you refer to this one, we have negative omega squared. So what we're going to do now is we're going to take out that negative omega squared, so that in here we will only left out with v1 and v2. So if I take negative omega squared out, okay, we can write this equation as metric as negative omega squared 1, 0, 0, 1. And look now, this one has become v1 and v2 plus k1 plus k2 over m1 negative k2 over m1 negative k2 over m2 and k2 over m2. And this one has also changed to v1 and v2, in which we can solve it mathematically. So the aim to develop characteristic equation is that in the end, what we're going to have is that we're going to have A minus lambda I. Okay, this is our final aim in order to solve goes to 0. So this is what we aim, whereby this lambda is what we call as eigenvalue, and eigenvector is the V itself, which is the mode shape. So from here, how to change this into this? So if you look here, this is matrix A, we got lambda, and we got identity matrix. So what is lambda? Lambda is eigenvalue, and eigenvalue can also write as omega squared. So lambda is equals to omega squared. If you realize here, we've got our lambda here. This is our lambda, and this is our identity matrix, and this one is actually our A matrix. So we rearrange it in order for it to be matrix A minus lambda I multiplied by matrix V. So we can write it as K1 plus K2 over M1, negative K2 over M2, negative K2 over M1, K2 over M2, minus our lambda, which is omega squared, okay, multiply with identity matrix, which is 1, 0, 0, 1. And because this is a mathematical operation, so outside here is matrix V1, V2, which is equals to 0. So this is what we call as characteristic equation. So again, to recap, characteristic equation is in the form of this equation, whereby it is actually matrix A minus lambda I multiplied with V. So lambda is what we call as eigenvalue, okay, or known as omega squared. I is the identity matrix, and V is what we call as eigenvector. So what is matrix A? Matrix A is actually the stiffness matrix over the respectful mass, right? So that's all for this session. So in the next session, we're going to look on how we're going to get the values of eigenvalue and eigenvector for different cases. All right, so I'll see you again in the next session. Thank you very much.